Okay, I'd like to just go over quickly how to determine velocity from tidal forces. Now, this is how you do it if you were in a box, in an accelerating box, and you wanted to find out if you were on a planet, and you wanted to find out some information about that planet. But it's also something you could do if spatial acceleration caused tidal forces, then you could figure out your absolute velocity using this as well, which means spatial acceleration probably almost certainly doesn't provide tidal forces. So just very quickly, let's say you're in a 1 kilometer long spaceship and you're accelerating at 10 meters per second squared or 9.8 meters per second squared, okay? We'll have to be a little more precise, actually. Let's just say you're at 9.8 meters per second squared, and there's some long, determined to some long degree of accuracy. You have an accelerometer here in this part of the spaceship, okay? That's my accelerometer. And then this is 1 kilometer, and then you have another accelerometer here. And you notice that there's a slight difference between, and this is 9.799 something or other. Well, first of all, that's your tidal force. That tells you that you might not be in a spatially accelerating object. Actually, so we don't know. Let's take this off. So we don't know. But there's some acceleration this way, and you can feel the force. There's a force pulling you, this way, and you don't know what type of force it is. So based on this, you can calculate, so the acceleration equation is just gm over r squared for a planet. And so theoretically, if you were on a planet, there'd be some r here, radius to the bottom of the planet. And then this would be gm over r plus 1 kilometer squared. And so this would be your two accelerations. And then I thought it would be easy, but it's actually pretty complicated, a bunch of operations to get from here to the calculating the radius of the planet. So I just did it. It involves quadratics. So basically, the radius can be calculated by equals 2 times, this is a pretty good approximation, AC1 over AC2, call this 1, call this 2, minus 1, okay? And this gives you equals the radius of the planet, this R1 value over here. Or you can use the R1 to calculate the GM and figure out, and then use that to calculate escape velocity, which would essentially be how fast you're going, okay? If it was instead you were in a spatially accelerating field that experienced tidal forces. And you're not supposed to be able to do that. That violates Einstein's relativity principle. So it probably doesn't happen, right? But this is a very important principle to understand, because it is if you do see in tidal forces in a spatially accelerating field, it would be very interesting to characterize that. Does the gradient always equal GM, or is there a different gradient? Does the gradient change with acceleration? Okay, just going to add an actual calculation. So this is your rocket or your object. There's a 1 kilometer separation between the two accelerometers. The first accelerometer reads this long number. The second, well, not long, but well, yeah, number with many significant digits. The second one reads another number that's slightly less. The question is, what is R1? What's the radius if this was a planet? If this was sitting on the surface of a planet, and this was the acceleration, and this was the tidal force, the difference was the tidal force. What is the distance R1? Well, R1 equals 2 over A1 over A2, the ratio A1 minus 1. which is going to equal, if you do the math, it basically equals 6.378 kilometers, which just happens to be the radius of Earth. Of Earth, okay? Anyways, just, I guess I'll write down, let's say you had a planet that was 10 times the mass of Earth and 3.3 times the radius, or you would get these numbers. You'd get 9.7842,997. But then here, the second one, A1, and then A2 would be 9.797. Yeah, that's right. 458.1 meters. These are meters per second squared, obviously. And then R1 in that case would be 2A1 over A2 minus 1 equals a radius of 20,169 kilometers. Okay, so works in both cases. But if but here the ratio here, then you can use this ratio to calculate the EV. So then you can use R1 to get GM, and then you can calculate EV as square root of 2 GM over R. So you can find your velocity in space, as well as the mass of the planet. But the key is you can calculate your velocity, and you shouldn't be able to do that. Okay, thanks.